Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Buonasera a tutti. Today we have Roberta Anna ISEPPI da Göttingen, and she will walk us the first steps towards the quantization of the spectral action, the Batalin-Vilkovisky construction for finite spectral triples. Roberta, it's all yours. Take it away.
Okay, thanks a lot, Piotr. Thanks also for reading the very long title, but you see, I really try to put there all the keywords that I'm going to use and present during this talk. So let's say what is the program. So as I said, I'm going to present the different part of the title. I will start with telling you something about this BV construction that is also known as this Batalin-Vilkovisky quantization procedure. And I will start by telling you what are the motivation, why one want to develop all this kind of machinery that, as you are going to see, is made out of a few steps and is a bit complicated. But the take-home message is that the reason for dealing with all of this machinery is really trying, so the goal is trying to quantize the path integrals, so to quantize a gauge theory via a path integral. So, and what will be clear at the end is that the core of this Batalin-Vilkovisky approach is the fact that we are somehow treating the theory from a cohomological perspective. So cohomology will definitely play a key role. Then I will say something, but probably more brief, about non-commutative geometry. And the most important part will be really trying to describe how can a spectral triple be related with gauge theories. And then I will try to put the two things together and to present you my result that consists indeed in describing this Batalin-Vilkovisky construction for the case of finite spectral triple. And this will have both the side of this, BB extension, as we are going to see, as well as the cohomological aspect. Okay, but let's start from, the context. Where are we? So the idea is that last century started with these two big groundbreaking theories, so general relativity on one side and quantum mechanics on the other side. And if one look at them, they are really so different one from each other, in the sense that while general relativity gives really a deterministic description of the gravity in a dynamical space-time and really force us to change our idea of what means time, what means space. The revolution put that the quantum mechanics had and pose was the introduction of two important concepts. So the idea that when we look at nature at atomic and subatomic level, this is really governed by probabilistic law. So there is no determinism anymore. And the second ingredient is non-commutativity. And as we all know, there are problems in trying to put these two theories together and to try to describe gravity at a small scale. And then an idea can be, say, okay, we can't really have any experience and experiment guiding us in such a small scale. Let's try to just, working out the mathematical formalism and trying to really look to the notion of quantization from a mathematical perspective. And of course, there are many ways to describe a quantization procedure, many techniques, but all of them have exactly the same idea and the same goal. So you want to start from a classical theory that is usually indeed macroscopic and is characterized by the fact of being usually deterministic and commutative. And through this procedure, through this technique, through this quantization, arrive to a description of a theory that at this point is microscopic and is probabilistic based and non-commutative. Okay, having this as a background, let's put the second ingredient on the table, namely the notion of gauge theory. So gauge theory play a key role in physics, and all the four fundamental forces, like a gravitational force, the electromagnetism, the weak and the strong interaction, all four of them can be described as these gauge theories. And from a mathematical perspective, just to have an idea, a gauge theory is just a theory with some symmetry. So some symmetry that exists from a mathematical point of view, but that cannot be viewed through experiments. So this is going to be the definition we are going to use for the rest of the talk. So for us, a gauge theory is going to be a package of three elements. So this X0, S0, and G. And X0 is what I will go to refer as a field configuration space. S0 is the action functional that is defined over X0 and will take values in R. And the third element is this gauge group, and this is what we are going to use to indeed encode this idea of symmetry. So we have a group acting on the configuration space and leaving the action functional unchanged. So the idea is that if we do evaluate this action function on any point of the orbit of this gauge group, the result is the same. So, and this is somehow describing this idea that wherever we are on the same orbit is absolutely identical from a physical perspective. So we cannot distinguish.
So just a quick question, this field configuration space, is there some kind of topological space or?
Oh, I will put some extra structure on a second on that. Yes. So
Okay, so now it's only a name, yes?
Exactly. For now, it's just somehow a package of object, and but yeah. So there is still not math on that yet, but it will appear in a second. Yes. Okay. Then what I was trying to convey is this idea that it's really the presence of these symmetries that create problems when we try to quantize a theory. And one of the way of quantizing theories is via this so-called path integral approach. So as I was mentioning earlier, so one of the revolution coming from quantum mechanics is really this idea that if we think about we have a particle in some point in space, we cannot really predict deterministically what is going to be the trajectory of this particle. So this is why there is this picture on the right of the slide. So as I said, if we manage that, imagining that there is a particle in A at a certain time, the only thing that we can try to compute is what is the probability that this particle is going to be at the point B after a certain amount of time. Because we cannot really predict the trajectory, what we have to do is somehow to consider all possible trajectory and to integrate over all of them. And it's via this integration over the path that one can compute indeed this probability of finding a particle in the point B after a certain amount of time. So this is how the intuition behind the idea of a path integral, of course, the notion developed over the decades. And nowadays, if you want to quantize a theory via this path integral approach, what you ended up computing is integrals of this kind. So here, this G denotes indeed the expectation value of a regular function G on the configuration space, so some observable, something that one can compute, and this is supposed to give you a number. And the other ingredient is this partition function that appears. Okay.
Silly question. What these paths are in which space?
Yeah, so as we are going to see in a second, so of course it really depends what is your approach, what is the mathematics that you put behind. So for us it's going to be like a manifold, but in general it's something more complicated, and it really.
I wasn't asking about such technicalities. I was asking, is it these are paths in X0 or the space of paths is X0? I'm confused.
Yeah, sorry. So yeah, so the idea is that you're integrating over the path. So yeah, your configuration space is the space of path. Yeah, you're integrating over that. Yeah. But
sorry, And so the existence of this measure is very problematic. Am I right?
Absolutely, absolutely. Yes. So as I said, so this is the intuition behind this integral, but it actually makes sense as an integral. So it has a well-defined measure only if you are actually in finite dimension, which is not the context that you use for quantum field theory. For quantum field theory, of course, we go infinite dimensional. And yeah, so this is the reason why this measure appears in red, because it's actually not well defined. And this is why there are different approaches in trying to indeed deal with this integral. And one of them is this Fontarier approach. You might have heard of that. Is what is at the base of topological quantum field theory. So the idea is that we have an integral in infinite dimension, and we have no idea how to define it. But we know that if we restrict it to the finite dimension, this is the normal integral. It makes sense. So this approach tells that a way to define something that is not well defined is by imposing its satisfied properties that we know exist in a finite dimensional case. And in this case in particular, what one does is to impose that this integral infinite dimension not well defined satisfies the Fubini theorem. So the idea is that you have a complicated domain of integration and you cut it in pieces all the way up to the point where you reduce that to something you can compute. And you define the initial integral as, coming from all these pieces together. So you're imposing that your infinite dimensional integral satisfies the Fubini theorem. But what we're going to use is actually the second approach, same idea. So we impose that our not defined integral satisfies a property that is usually defined and satisfied by the finite dimensional one. And this is the perturbative approach. And the idea is that what one imposes is that if we take the parameter h bar, so the Planck constant, to be going to 0, then we can approximate the integral as the sum that appears here. So you see is a long sum taken over the set of critical points of S0. S0 appears here as exponential of your integral. And all the remaining piece, you see, depend on the value of your action in the critical points, on the determinant of the Hessian, and on here you see there is small blue gamma, the Feynman diagrams. So the Feynman diagrams are somehow a way of labeling the possibilities or possible options for the particles, because of course when you are in quantum field theory, you know that particles can be created and annihilated and they can interact. But all of this can just be somehow described using these diagrams. And what enters in this formula are, for example, the Euler characteristic of the Feynman diagrams, or the cardinality of the automorphism group, and the last ingredient are some weight. So the idea is that then what matters is just to consider the critical locus of S0 and then a bit of combinatorics with the Feynman diagrams. And this approach turned out to be extremely powerful from the point of view of experiments. So people doing experiments found very good results with this approach. But there is a problem. So in order to be able to implement this perturbative approach, we need to indeed approximate our integral with a sum that is taken over an isolated set of critical points, and regular, because you see we are taking the square root, actually 1 over the square root of the determinant of the Hessian, so we need some regularity for these critical points. And that's actually not what happens if we consider gauge theories. As I was telling you earlier, the idea of a gauge theory is that from a physical perspective, anywhere I am on the same orbit of of my group, so it's equivalent from a physical point of view. So this implies that if I do have a critical point, then I have actually a full orbit of critical point. So that's clearly not isolated and nor regular. And here is where the BV formalism comes to help us. And the goal is somehow to eliminate this redundancy coming from the symmetry, but without changing the physics. And of course, the first instinct is just to take a quotient. Because, of course, if anything on the same orbit is equivalent, I just quotient by the action of the group. But often this kind of integral gives objects that are not super treatable, even more when we try to do integration over that. So the second approach is actually at the opposite side of the spectrum. So if we cannot get rid of this, redundancy, why we don't just add more variables? And these variables are usually called Gauss fields. And of course, intuitively, one might think, okay, why I don't want to add more variables, make my life more complicated. But here I'm just giving you an example that is a trick that is often used. So if you want to compute, the Gaussian integral on R, you just go in 2 dimensions and use polar coordinate and everything is nice and fine. And that's exactly the same spirit. We are going to add more variables. And August is going to be just an auxiliary variable characterized by 2 numbers. The first is the so-called Gauss degree, it's just an integer. And the second is the parity that can be either 0 or 1. And 0 described like the so-called bosonic parity. So for us, it's just a real variable. And 1 corresponds to the fermionic parity. So we're dealing with Grassmannian variables. And of course, we like that the parity of the Gauss degree is actually the parity of the field we are considering. Okay, so just to give you a bit of coordinate, so everything started with Favre and Popov. They were the one having this intuition of trying to eliminate this divergence by introducing extra fields, and they were the one calling them Gauss fields. And often the people refer to these Gauss fields as indeed the Favre-Popov ghost. And what they were doing were studying Yang-Mills theory, and they had this idea indeed of adding the variables, having as a final goal the fact of being able to, then do a gauge fixing procedure and finally apply the stationary phase formula. So the goal is always find a way to apply the stationary phase formula and having an action functional with isolated and regular critical locus. Later, what I wanted to mention is that what they did was just to add the fermionic Gauss field of Gauss degree 1. And the idea is that indeed the first thing that one adds are indeed Grassmannian variables. So we are, as soon as we're adding Gauss, we are in a graded world. After that, Becky, Ruther, Stota, and Tutin they made 2 discoveries actually. So first of all, they noticed that there are cases where it's not enough to add this Gauss of degree 1. And one might actually end up having to introduce Gauss and Gauss for Gauss. And this is related to the kind of symmetry that you're dealing. So somehow the idea is that you don't have independent symmetries, but you have symmetries among the symmetries. And in order to deal with this redundancy among the redundancy, you might need to add the Gauss for Gauss. And the second thing that they put on the table was the cohomological approach. So the idea is that indeed there is, so one can describe this BRST-BV formalism as a cohomological approach to the study of gauge symmetries. And for example, one can see, there is this BRST cohomology. So if you put yourself in the easiest case where you have somehow independent symmetries, so only ghosts of degree 1 are needed, the BRST cohomology is nothing more than just the Chevalier-Eilenberg cohomology. However, as soon as you put more ghosts and the situation gets more complicated, also the cohomology gets more complicated. So you have indeed generators of higher order and so on and so forth. The next step in the story was the introduction of an anti-bracket structure, and we're going to see in a second why that was important. And finally, there were the work of Batalin-Vilkovisky, so that they gave the name on the entire construction. And their intuition was the idea of not only introducing ghost, but also introducing anti-ghost. So somehow doubling everything you're doing. So if you have a ghost, the idea of an anti-ghost is just to introduce a corresponding field that is going to be denoted with this phi and the star. And given a field, given a ghost, the corresponding anti-ghost is again characterized by two numbers. Once again, the ghost degree. The ghost degree of an anti-ghost is minus the degree of the ghost minus 1. And the parity of the anti-ghost is the opposite parity of the ghost. And
Rim, I have a quick question.
Sure.
I don't know whether I recall it correctly, but you said that this epsilon corresponds to, in case of 0, corresponds to bosons, yes, and 1 corresponds to fermions. So this is something like supersymmetry, or?
So adding the anti-ghost is somehow enforcing. So from a mathematical perspective, you're somehow constructing a cotangent bundle situation. So it's just going to be helping in the construction. So from a physical perspective, it's only this ghost and ghost for ghosts that somehow encode something like this, the symmetry and how there are like symmetry among symmetries and so on. This doubling procedure has more mathematical flavor, and it actually allows to carry on the construction, having at the back, this kind of, cotangent structure. So you're really somehow doubling, cotangent bundle structure. And it's actually somehow the way of enforcing a natural Poisson structure and brackets because as we are going to see in a second, it's more like a mathematical trick, but it's not supersymmetry.
Okay.
Exactly, yeah. Because supersymmetry is related to Grassmannian variables. She has no Grassmannian variables here. It's not supersymmetry.
Oh, we do have Grassmannian variables, so the ghosts are going to be Grassmannian, but still is not supersymmetry.
Okay.
Yeah.
Okay.
Okay, so let's just try to point it out what is the first step. So we start from our theory. So our theory is our gauge theory. We have configuration space, action functional, and gauge group. And what we want to obtain via this BV extension is a new pair that we call this BV extended theory. So we have a space that is our initial space, and to that we are adding ghost and anti-ghost, bosonic and fermionic, with this parity coming from the degree. And also the action functional is going to be extended. So our S0 is going to be extended to this S tilde. So it's S0 plus other terms. And these other terms, of course, involve these new variables we are adding. And this is done in such a way that we are eliminating the redundancy. And I'm explaining that in a second. But first, as I said, that was more like the intuition of what is happening. If one wants to put a bit of math, one of course has to decide what is the structure on the configuration space, and what are the classes of what we are considering. And here I try to give you a bit of an overview of what are the different approaches. So this is why if you hear different people telling you about the Batalin-Vilkovisky formalism, you can actually hear very different stories. So I would put myself more in this kind of differential geometric setting as for what I'm going to explain you in a second. But then, of course, the aim of the talk would be to have a last arrow appearing where we can also put a non-commutative geometry as an approach to that. But what is the idea behind this formalism? So remember, we have a goal that is to compute an integral via this stationary phase approximation. And the problem is that if we want to do that for gauge theories, our action S0 has orbits of critical points. Now, we are now introducing new variables, and somehow the intuition is that we are going higher dimensional and giving ourselves more space. And adding these extra dimensions, we want to use them to have the space for deforming both the configuration space and the action functional. And as you see in this picture, the result of this deformation is that we are aiming to indeed have a critical locus that is just made of isolated and regular points. But of course, we want to be sure that we're not changing what we are computing. And this is ensured by this theorem that is indeed due to Batalin-Vilkovisky. And this theorem says that what we want to compute, so exactly this integral here, clearly depends on the domain of integration, so depends on this x0, and of course depends on s0, but not so tightly, in the sense that we have a little bit of freedom in changing the configuration space, as well as changing the action s0. And this integration doesn't perceive this change, so it's invariant if we actually do change x0 to any other L that is a Lagrangian submanifold that lives in the same homotopy class of x0. So we can deform x0 up to homotopy. And for what concerns this S0, that can also be changed and became this SQ. And the only condition is that this SQ is in the same cohomology class of our S0. So, I mean, it's a weaker condition, where this cohomology class is this so-called quantum BV cohomology. So the idea is that we have two parameters. And this, if you want to have a bit of the flavor, what is this theorem, can be looked at as some kind of Stokes theorem for graded manifold, because our x0 is, as I said, a starting manifold, and we are adding variables that can also be Grassmannian, so the context is the one of graded manifold. Okay, then that's the strategy. We just need to find a new Lagrangian submanifold in this space of ghost and anti-ghost, and a new SQ that is actually asked to be a power series in H bar, whose coefficients are ghost and anti-ghost, such that the cohomology class is a Q, BV cohomology class of S0 coincide with the one of this our new function. Equivalently, I mean, one can also ask that this SQ is a solution of the quantum master equation, so something that looks like that. So you see that here I'm using this Poisson bracket, so this structure just comes from, naturally saying that the only combination that is not zero is between a ghost and a corresponding anti-ghost. So it's really like the standard that you would have on a cotangent bundle. And this nabla, so it's not going to play a big role in the following, but just for telling you some kind of Laplacian in this context of graded manifold. So the strategy is to look for these two objects, so the Lagrangian submanifold and an action SQ, so that if I do study the critical locus of SQ now on this new Lagrangian submanifold, this is isolated and regular. So, as I said, so the theorem allows us to tune these two parameters. And the reason why we were not able to compute the integral is somehow that we got the wrong representative in the homotopy class of the Lagrangian submanifold and in the cohomology class of this S0. So we just have to find and to tune these two parameters well to find the right representative, and then compute the integral as we know, so with this kind of stationary phase approximation. Okay, so that's the idea of this BV theorem. But let's put a little bit of structure so to know exactly what we're dealing. And as I said, I'm going to describe it in easier cases, so some kind of globally flat graded differential setting.
Excuse me, may I have a short question? For a moment, I lose the internet, but I just realized that you are talking about Lagrangian submanifold. Maybe at the time that I lose the internet, did you assume some kind of symplectic structure on a manifold that you are talking about Lagrangian submanifold? Because I observed that in the definition of gauge theory, you say that X is a manifold, not necessarily a symplectic manifold. So I wonder, what do you mean by Lagrangian submanifold?
Yeah, I mean, I'm going to describe that in a second. So we are actually going to take advantage of this, let's say, cotangent structure, and we are going to take our Lagrangian submanifold as given by a gauge fixing, and one can prove that indeed that this via this gauge fixing. So the kind of manifold you describe is indeed the Lagrangian submanifold. But I'm going to show you the formula in a second. So I hope that this clarifies more. Because I was saying it's the moment to put a bit of structure on what we are doing. So the initial theory is just our gauge theory. We're in the simplest example. So we are considering vector space as a configuration space. And the action functional is just going to be a polynomial that can be viewed as just like element in the structure ring of our affine variety. And as a gauge group, we are taking UN. Okay, so what is this BV extended theory? It's asked to be a Z-graded supervector space that is suitable to be decomposed in this way. So I want this to be a direct sum of two pieces, where F is a graded locally free OX module whose homogeneous component have a finite rank. And the fact that I can indeed split in this X tilde in these two parts is really encoding this idea that I'm doubling the entire story. So on F, I do have all my ghost fields. And in this F star shifted by 1, I do have all my anti-ghost. And you see it's really somehow implementing this duality condition. The second condition is that I want to keep my physics in degree 0. So this is why the notation actually affects 0 is really taking care of this. For what concerned S tilde, of course, is going to be a regular function involving all ghosts and anti-ghosts, total degree 0. And once again, I have the condition that if I do restrict that to the initial configuration space, I can recover my initial function. And here, the other part of the condition involves this Poisson structure. And as I was telling earlier, you see the only option for two generators not to have a 0 Poisson bracket is that we are actually pairing an anti-ghost with a corresponding ghost. And it's really somehow, like the natural Poisson structure really coming from this doubling condition. So the third condition we are imposing on S tilde is that it is a solution of the classical master equation. And that plays a key role because it's exactly the condition that allows us to say that each time we do have an extended theory, this is a BV extended theory, it naturally induces a cohomology theory, and that this is called this BV complex. So
sorry, Roberta, please go back. I'm completely lost now. What is F? What is F star? I mean, I try to understand how you get this extension. What is this square bracket 1 as a subscript? I completely don't understand what you write.
Okay. I will go back here. So so the idea is that I do have my extended configuration space that needs to contain my ghost and my anti-ghost. So this condition of having X tilde as this direct sum of these two pieces wants to encode this idea. So my F is going to represent all my ghosts. And of course, it's going to be an object, a graded object. So it's going to be like the not negative part of S tilde. So in degree 0, F as my initial fields. In degree 1, I have my ghosts, which are like Grassmannian variables, degree 1. In degree 2, I have the ghosts of degree 2, which are real, and so on and so forth. And my condition is that in each step, I'm only introducing a finite number of ghosts. So this is why I'm saying that homogeneous component of finite rank. So in each degree...
So wait, so F is a module, right? It's module over this S0, which is a polynomial algebra.
Mm-hmm. Yeah, so I allow myself to multiply for the field. So that's going to be needed in the following. So... but the idea, as I said, is that F is for the ghost. And then the notation here, let me explain it. So F starred shifted by 1. So I'm introducing for each ghost the corresponding anti-ghost. And the notation for the ghost is just adding a star. So this is the space of all the anti-ghosts, and the shift is just a shift in the degree. So the initial fields are in degree 0. For the initial fields, I also have to introduce, a corresponding anti-particle, anti-field, and I don't want that to overlap, because you might remember the ghost degree of an anti-field is minus the ghost degree of the field minus 1, exactly for this reason. So if I would just, doubling in the negative, what is in degree 0 will stay in degree 0. But these anti-fields I'm introducing are also not physical, so I want to shift them by 1, so I'm not confusing what happens in degree 0. So this is the reason why I do have this shift, just for keeping separate the different parts. And in degree 0, I have my initial fields, degree -1, anti-fields, -2, the anti-ghost, and so on and so forth.
And what does it mean, this notation?
Oh, no, this is just the note here. It's some kind of footnote.
Oh my goodness, this is very confusing. I've never seen anybody making a footnote inside an equation. Sorry.
Yeah, okay, that's a good feedback. I was not. There was also the colors. So now you see that there is the red, and then the tree. So this is the notes were appearing in correspondence with the part. Okay, sorry, I was.
Okay, so that's much better now. But I'm still confused. So what is x tilde bracket 1 million when I is equal to 1 million? What is it?
So the Z gradient is taking care of, is the ghost degree. So in degree 0, you have an initial field.
Yeah, in degree 0, I know what it means. And what is in degree 1, 2, 5, -5?
Yeah, so of course the question is how do we determine how many ghosts we are adding in each degree, depending on our theory. But of course it depends on what is the theory we are starting with. So in degree 1, you have the generators of the symmetries. In degree 2, you have the symmetries among the symmetries. That's the philosophy of the story. So you're adding new variables for killing symmetries.
Yeah, I understand it mathematically, not physically. I'm just wondering, so does it come from the module structure? Am I correct to think that the positive part of the gradient comes from F and the negative part of the gradient comes from F star?
Correct. Yes. Exactly. So in F you have the ghost, and in F star you have the anti-ghost. Positive and negative. Yes. Correct. Okay. If there are no other questions, I might continue. And speaking about this cohomology situation. So the idea is that each time you do a BV extended theory, you can construct, and it's natural in this ABV complex. And for what concerns the cochain space, it's here. So it's the cochain in degree I are just the part of degree I of this graded algebra. And if one wants to write it explicitly, it's just some element of degree I of the graded symmetric algebra generated by all these pieces. So here W have the ghost, anti-fields, and the anti-ghost. And for what concerns the coboundary is computed over a generic cochain just by taking this Poisson bracket with a tilde. And the reason why this is in red, so the fact that this is indeed a coboundary operator, is related to the fact that S tilde is a solution of the classical master equation. So it's solving this equation here. So if you apply twice D, you will see that this is 0 exactly due for that condition. So somehow the construction up to now is made of these two steps. So one first step is this extension via the introduction of ghosts and anti-ghosts, so this enlarging of the space. And the second step is this construction of this BV complex. And the reason why this is interesting is that it actually contains some physical information about the initial theory. In particular, for example, if you look in degree 0, what you can recover are the classical observables of your theory.
But sorry, and what is this Poisson looking bracket? I understand that S tilde is now a function on X tilde. But
Exactly.
what is the meaning of this red bracket?
So these brackets are just, I mean, I think that, yeah, it was written here.
Okay, yes. Yeah, okay. Okay,
This is
thank you. I
that.
just forgot it. Yes, thank you so much. Yes, so poisson. Okay, fine.
Yeah, exactly. And then, of course, the natural question is how do we know how many ghosts and anti-ghosts we need? And how do we construct this still there? So there are different methods. So here I'm just recalling some used. So a possibility for determining the ghost sector is by computing a consultate resolution of this Jacobian ideal determined by S tilde, while S tilde is constructed by approximation procedure. But I mean, it gets complicated at this point. So we will see just an example in the following. But as I already said earlier, what matters is really that the ghosts have to deal with the symmetry. So of course the symmetry also appear on how S tilde is S0 is written. So it's really the space of ghosts related to the symmetries of the action. And then, fortunately, there is a small technical detail. So the idea is that we still, we are at the point that we enlarge our space, and we still need to find this Lagrangian submanifold. So that's our goal. So we do have a candidate for a new action, but we are still looking for this Lagrangian submanifold. And the finding of this Lagrangian submanifold is usually done by performing a gauge fixing procedure. And that's somehow the idea. So one looks for a gauge fixing fermion that is denoted by psi, traditionally denoted with the capital psi, which is asked to be a function only of the ghost. So we need to cut into the space. So it's a Lagrangian submanifold. So we need to get rid of half of the dimension. So we're going to take something that only depends on the initial fields and the ghost. And then our L is going to be defined as the manifold where these equations are satisfied. So the equation it says that, okay, if I do take the partial derivative of my psi with respect to the ghost, this should be equal to the corresponding anti-ghost. That's clearly a set of equations, and it cuts into the space of variables, and we actually don't have anymore these antifields. And that's actually the role played by the antifields. So really make all this construction very algorithmic somehow. So you just look for the psi that gives you this nice set of equation and finding the right Lagrangian. And yeah, the technical detail is here because you might have not noticed. So I'm asking for something that only depends on the ghost. But for now, the ghosts are only in positive degree. So this intermediate step requires to even enlarge further the space to having also auxiliary fields. And that has to be done properly. So we don't want to change the cohomology. And this is done by introducing contractible pairs in cohomology. And, the number of them is depends on how many ghosts and what was the highest degree of the ghosts that we introduced. And here is just for, having more or less the idea where we are. So this step is the last one that we are taking. So this further extending of our total space via these auxiliary fields. And we want to be sure that we're not changing the cohomology because the cohomology carries some information that we don't want to change. So the idea is that these auxiliary pairs are just, characterized by this kind of condition. And then the only free parameters is the degree of B, because as you said, the degree of age, the second element in this pair, is determined by the degree of B plus 1. And then, of course, the parity comes along because the parity is the parity of the ghost degree. So it's just one parameter. But that's enough because it's enough to say, okay, let's take the degree of B equal to -1. That's a ghost of degree, negative degree. And then what the procedure says that you start with your BV extended theory, you add this pair. And of course, you don't want to change the structure. So of course, adding this pair means that you're also adding the corresponding anti-ghost. So you still have this doubling. And for the action, you're just adding this trivial part. And this is exactly what allows you to say that at the level of the cohomology, nothing gets added. And all of this is just enough. So you know what are like the level of the reducibility, and so how many ghosts, how many auxiliary fields, all that can be done. And it can be done in such a way that for sure nothing physical will depend on the choice of psi. And that, of course, is something that one wants to be sure. So you don't want to change a physically relevant quantity by picking one psi or the other. But this kind of construction allows full freedom on the choice of psi. Okay, so that takes us to the end of this construction. So because now we have everything is needed for implementing the gauge fixing procedure and finding our Lagrangian submanifold, which is indeed defined by this gauge fixing condition. And the last cohomology entering is this BRST cohomology that now is only determined by the ghost. And as a coboundary operator, just the restriction of the BV coboundary operator on this Lagrangian submanifold. I know that was a long story, but this is a summary of what is this BV construction. It's a bit complicated, made of a few steps. But the idea is that you start from an initial theory and you want to extend it. And you extend in a way that you are somehow taking into account what are the symmetry of your theory. So you're adding a ghost in this first step, ghost and anti-ghost. And these are what are really carrying some information, and this is why this BV complex is the relevant one. The next step are only technical steps that you have to take in order to be able to find this Lagrangian submanifold where you want to integrate. So this step is just adding some extra variable for convenience, but in a way that you're not changing the cohomology. That is what you want. And this gauge fixing is the last step, is finding this Lagrangian submanifold where you want to integrate. And what is interesting is that there is still some property captured also when you actually reduce this complex to this smaller complexes. So while this BV complex is two-sided, the BRST complex is one-sided, so it's way easier to compute. And this is, as I was saying, important, all this part on the cohomology, because in degree 0, we saw this described the classical observable of the theory, but in a higher degree, one finds abstraction to the quantization, which is also somehow relevant.
And sorry, this abstraction is realized in some particular I, or?
It's in degree 1 actually. So in degree 1 you find the abstraction. Yeah.
Somehow I recall that this theory of deformation quantization somehow lives in H3, but I believe it was Hochschild cohomology. So this is a different story, yes, completely.
Yeah, it's a different story. Yes.
Okay.
Okay, so if you're all fine with that, that was more or less a crash course on the BV construction. And then now we move to non-commutative geometry. I think that this is all familiar for you, so I will probably be a bit quicker. And but what I wanted to draw your attention on is the part of non-commutative geometry that indeed goes towards gauge theories. So, I mean, we of course started with this idea of quantization. This is why we are here and dealing with this Batalin-Vilkovisky formalism. And as mentioned already, so we have gravity on one side and we have, fundamental interaction on the other side. And while gravity deals with the curvature of the space-time, so something that is continuous in nature and also commutative, because, the right framework to describe gravity is Riemannian geometry, so it's definitely commutative. If we pass to study what happens at the microscopical level, we have something that, deals with a discrete nature, so particles, and is the non-commutative in nature. And then the idea is trying to put everything together and finding a unifying background for these two situations. And of course, I mean, I think that if we all discuss about non-commutative geometry, we have a different way of describing it. So the way how I like to see it is some kind of enlarging of classical differential geometry. And of course, one can say, okay, let's try to describe, a manifold in some kind of algebraic terms. And while topology and differential geometry are usually dealing indeed with topological spaces, and differential geometry speaks about the points and charts and something that looks like Rn. If we go to the algebraic side, we want to have this described in terms of sister algebras. And this is why I was saying that it can be seen a unifying framework for the finite, non-commutative and infinite commutative cases. So because of course sister algebras can have these different natures. Yeah, I mean, I don't know whether there were students or not, so I thought it doesn't hurt to just recall the definition of sister algebra, but it's nothing more than that. But then, of course, the key part of the story is the Gelfand-Naiman theorem that puts this kind of equivalence between speaking about locally compact Hausdorff topological spaces on one side and commutative sister algebras on the other side. And while the passage from the topological space to the sister algebra goes in associating, the sister algebra of continuous function over x0, perhaps, going to 0 at infinity. The other side of the story takes the sister algebra in the structure space of A with the weak topology. And of course, the key point on this story is that we're speaking about commutative sister algebras. So of course, the question is what happens if we go non-commutative? And this gives us non-commutative topological spaces that they're not so nice to draw actually, but yeah. And of course, if one's go to the metric aspect, there is a famous reconstruction theorem by Kahn that says that one can proceed with the same idea. So trying to find an algebraic description of manifold, in particular a closed connected Riemannian spin manifold. And the corresponding translation in algebraic terms of this object is a so-called real spectral triple. It's actually an even real spectral triple, which is clearly not a triple because it has more ingredients, where the algebra is asked to be commutative and then 8 axioms are required to be satisfied. Here I'm just recalling the definition of a spectral triple, where a spectral triple as the first element it is an algebra, it's an involutive algebra. Second element is an Hilbert space, and my condition is that the algebra should be represented as operators, bounded operators over this Hilbert space in a faithful way. And the third ingredient is a self-adjoint operator over age, from age to age, satisfying few conditions from some kind of analytic regularity. Just for completing, giving you also what is real structure. So what allows to speak about the even spectral triple. So is this Z2 grading over age that is required to satisfy this condition with element in A and with respect to this operator D. And then the last ingredient is this real structure, so denoted by J, and some kind of motivation. So one can see motivation for introduction of a real structure coming from the real K theory, or more analytic from a Tomita involution operator, or more physics as a kind of Majorana condition on the spinor. All of this takes you to the introduction of a real structure. Which is just some antilinear geometry on your Hilbert space. And we are going to see that that's actually going to be useful for us. It's so important to keep in mind. So it has a commutation relation between gamma and the element in A. So some kind of a zero order condition. So it's some kind of compatibility between a left action and a right action. And a first order condition that is involving the operator D. And moreover, there is this table that describes the K dimension of a spectral triple. and is somehow a table of signs, so plus or minus, for where J can be squared to either plus or minus the identity. J can commute or anti-commute with D, and J can commute or anti-commute with the gradient gamma, and these are the options. And this table can be seen as model also from the case of ordinary manifolds, and of course reflect what happens in real K-theory. But there is also another way of looking at that. It's more like a physical inspired and deals with spinors and Majorana spinors and Weyl spinors.
Sorry, could you comment a little bit more on this last remark about this Majorana condition?
I mean, it's no, actually, not in a finite amount of time. I think it was just giving you a bit of the flavor. But so you should think that the context where this was coming is the context of canonical spectral triple. So and over there, the Hilbert space is the space of L2 square integrable function on the spinor bundle. So when it was constructed, this reconstruction theorem, so the Hilbert space were the spinors, and it was created. So it's not so surprising that somehow the condition that one can put on the Hilbert space, because you see this real structure is an antilinear geometry on the Hilbert space. The gamma is a Z2 graded on the Hilbert space, so it's all structure you're putting on the Hilbert space. Because all of that was coming and was aimed to have this reconstruction theorem in the context of, Riemannian spin manifold, the Hilbert space was the space of spinors. You see why I need imposing, that, your vector is, if you apply your real structure once or twice, you get a plus or a minus. The changing of the sign for spinors. Yeah, so this is.
Excuse me, I don't know, but I'm meaning. I have in mind this physical condition. What is the physical importance of this Majorana condition? That was my question.
Oh, yeah. I mean, that's a bit complicated. Yeah, maybe we can discuss that in another moment. It's a bit complicated.
Okay.
I have a simpler question, but also concerning this slide, just one line above. Could you remind me, please, what this KO homology is? And do we have like an index pairing between KO homology and real K-theory?
Oh, yeah, okay. That's also big of the digression, yes. Yeah, so the idea is that so again, if the context you're thinking is the one of this canonical spectral triple, and the spinor bundle, at the back of that there is the Clifford algebra, the Clifford representation. Yeah, so all these 0 to 7 has to deal with the classification also of the Clifford algebras and this kind of periodicity. So I mean, you find the same table in this kind of context. But yeah.
But how about index pairing? I don't understand. Because you put it in one bag. Do you have an index pairing between KO homology and real K-theory?
I mean, you mean in general or in this context or?
No, in general. Or if not in general, what are the conditions?
Okay, I think that
because I know this KO homology is standard thing. I just forgot what it was, and just saying Clifford doesn't explain much to me.
Yeah. So I don't think I can really answer in the general case. So of course, once you make the jump in this set of spectral triple, this object became abstract object for you. So this was more for recalling that. So if you have been seeing the same table in different contexts, this is where it comes from. And then, of course, if you consider the spectral triple induced by a spin manifold, you do have, this table as this kind of feeling. So it comes indeed from...
Yeah, but I wanted to grasp concept. I understand what you mean by real K-theory, right? But I forgot what this K homology is really all about.
Yeah, I don't think I can really help you now with that. I'm sorry.
Sorry, may I have one more question? Somehow in physics, the fundamental symmetry, as is believed now, is this so-called CPT symmetry. So C stands for charge conjugation, P stands for parity, and somehow I think that these two corresponds to this J and to this gamma. But how about this T?
Oh, that's a very interesting question. Actually, there was recently a talk by Thomas Krajewski. He has been working exactly on that. So this kind of tenfold situation. So I think it's tenfold model, I think. It's exactly the story, and it's a decomposition of the two objects. So there is a correspondence between the real structure and the gradient on one side and the charge conjugation. So actually the J is the charge conjugation and gamma is the parity. And then is the composition of the two of them that gives the third symmetry. So yeah, that's a very interesting question. It has been worked out right now. I don't think that there is a paper, but there is a talk.
Okay, so the composition of J and gamma should be thought as the time reversal, yes?
Yeah, I think that's the story. I mean, of course, there are a bit of details that one has to check, but I think that what he proved is this.
Wow.
But
Wow.
I mean, as I said, for now, it's a talk, it's not a paper. So
Okay.
that's what I recall from what he presented. But yeah,
very interesting. Thank you.
There are tenfold situation that can be proved. Yeah, super. Okay, so the idea is that, I mean, here I was just briefly recalling you this axiom, but maybe in favor of the time, I will be skipping this part. I mean, because of course the story is that you need to add more structure. So there are these actions. So one is this finite summability, and is the way how you encoded the dimension in algebraic terms. So is if you do have your D, your self-adjoint operator, you can make a polar decomposition. And if you look to the sequence of eigenvalues, then you require some kind of decay, and this is how you describe in algebraic terms the dimension. There is the reorientability that has to deal with an offshoot cycle, and exists in Nash cycles, a kind of non-commutativity, a non-commutative volume form. And yeah, I was also, giving you a bit of the feeling of what is the sixth. So it's about a way of describing a guarantee that your manifold is connected. So somehow the idea is this: you do have this reconstruction theorem between a closed connected Riemannian spin manifold on one side and a very rich object, so even real spectral triple, where the algebra is commutative, and there are all these 8 axioms.
Just a quick question. I always thought that this irreducibility condition corresponds to the manifold being spin, and not necessarily general Riemannian. And somehow you have written that it corresponds to M being connected, so I'm a little bit puzzled by this.
Okay, yeah, I mean, I think that the point is that so it's based on this structure of this projection on the Hilbert space. So the fact that there are no trivia, somehow it makes it just one piece, but I don't know. Yeah, for me, I really thought that the reducibility was what described the fact that it's connected. But yeah, I mean, I might double check then. That's exactly how I remember it. But yeah.
I'm thinking about this spinor bundle, how it is constructed. So in general, you can always construct the so-called Hodge-de-Ram operator. But this is in some sense not minimal. If you classify all irreducible representation of spin, I don't know, spin groups or Clifford algebras, and those are of dimension 2 to the power of integer part of n over 2. So I always thought that this irreducibility corresponds to manifold being spin. So taking a minimal dimension of the spinor bundle. But maybe I'm wrong, I don't know.
Okay, no, I thought that there was another axiom for determining the spin nature, but yeah, I mean, I think we just have to check. That was my recollection of the story.
Oh, okay.
I think that connectivity of M has a simpler explanation because it is equivalence that there is no any non-trivial projection idempotent in the CS algebra A itself. Not, but I think that Adams is right. The irreducibility is equivalence to existence of S-spin manifold. So connectedness of M is equivalent to non-existence of non-trivial idempotent in A.
Yeah, in A, not in commutant of A. Yeah, exactly.
Yes, exactly. Okay.
Okay, super. Yes, so of course, I mean, I think that you know all the story, so maybe I can skip this part and telling you the part that matters for me, so how all this relates to physics, because of course, I mean, this is, let's go all non-commutative. Yeah, so this corner here of non-commutative geometry, the one that looks towards gauge theories and quantum field theory. So the idea is that each time you're given a spectral triple, you can describe an induced gauge theory. And the idea is that somehow we do have a...
Sorry, could I stop you one more time? Forgive me. You have written some interesting remark. Could you go to the previous slide? It is believed that spectral triples are not the right candidates for the objects in the category. I'm very confused by this remark.
So I'm of course not an expert in this specific categorical approach. So what was my understanding of the current ongoing research is that you cannot just consider spectral triple and have them as object of your category. They're somehow, because they couldn't really find the correct morphism for having spectral triple as object. So what I was told is that people are currently investigating the possibility of having KK cycles as object of the category, but then of course things get even more complicated, and I mean, you know, the analytical details are really difficult. So for what I know, there are people working on that, but I don't think that they've succeeded in finding a category for this object. And as I said, they're going more in the direction of seeing spectral triple as a particular subclass of object in a bigger category. But it cannot be just restricted to spectral triple itself. That is what I...
Is it something like spaces up to homotopy, or I don't know?
What?
For example, in algebraic topology, you have a homotopy category, which is that the objects are still topological spaces, but the notion of morphism is more flexible. That you admit somehow you identify things which are homotopy equivalent. So
yeah,
okay. In this spirit, or?
I don't know the details. I think that they are trying with a weaker notion of category, but the point is that is the analytical property of your object. And it's, I mean, if you know anything about this Kasparov product, it's really technical. So this is why I was putting that. So it's an interesting object, but the point of this slide was saying that, of course, we know what corresponded to the commutative case, and we decided to indeed reconstruct, I mean, like a spectral triple, but a spectral triple has all that structure and includes also, you know, this axiom, the commutativity. So we know that we can drop some of these options and have an interested object. But then, of course, that is a bit of a choice. So, of course, we know why we're dropping the commutativity of the algebra. But as you know, why we drop some of the axiom and some other we are keeping, and why we're keeping the real structure or the first order condition. So this is, of course, what is currently done in research, but one can also say, okay, but why we don't actually consider a more general object than that? And maybe the fact that we are not finding a right notion of category for spectral triple is pointing in the direction that we might look for something more general. But I mean, for doing physics, spectral triple are fine enough, That's more for people that are in this category approach.
Okay, thank you.
But it is true. I mean, there is a problem with the concept of morphisms between spectral triples. I mean, it's an old-standing problem. I remember it. And I remember there's also some work by people like Graham Mesland and I forgot who else, who try to represent, I understand, KK cycles by spectral triples, and this is quite a big production to be able to do so. Yeah.
No, exactly. I think that is a very long-standing problem, and also because it's very complicated. So I don't think that it still got solved. So, but that was the line of indeed going towards KK cycles and C. But anyhow, as I said, for me the corner is here. So spectral triple towards gauge theories. And as I was mentioning, the idea is that we somehow found a space, but we still had the dynamics. And if in the commutative case, a special role is played by the coordinates, because you have your manifold and your local charts and so on and so forth. As soon as we move in the non-commutative setting, the important data are the spectral data, and so the spectrum of your operator D. And this is where the spectral action principle fits. So the physical action can only depend on the spectrum of D. And this is the notion of spectral action. So spectral action is defined to be the trace of a function of D plus phi over lambda. So let's see the different pieces. So this phi is a so-called inner fluctuation of your operator. So it's an element that can be written as a finite sum of a product between AJ, which is an element in your algebra, and the commutator of D with another element of the algebra, with the extra condition of being self-adjoint. So phi star is equal to phi, where the star is the star of your star algebra. Lambda is just some kind of energy scale, and F is a test function, and only plays a role via this momenta. And the idea is that, of course, this trace is a trace of an operator. So you need to have that something here is a trace class operator. So this is why you need this kind of cutoff, and the function is something that makes that operator a trace class operator. And if one applies all this story, taking as spectral triple, the canonical spectral triple, so you have your underlying manifold, then the dimension is 4, and the momenta are just 3. And as we're going to see in a second, if we do consider that, for the standard model, these 3 momenta are just the coupling constant at the unification scale, the gravitational constant, and the cohomological constant. But we're going to see in a second what I mean with this. So the other thing to remember is that this is just the bosonic contribution. So gauge theories, of course, if one speaks about gauge theory, probably has something else in mind. So because classically, a gauge theory is understood as, principal bundle over a manifold, your space-time, and you speak about connections, sections, and the automorphism of the structure group. So these are the ingredients. But as we said at the beginning, for me, I don't need to have all this bundle structure, also because I actually don't have it. So I'm reducing the notion to its essence of having something that with some invariance. And then what can be a natural candidate to play the role of a gauge field in this context? So we have a spectral triple, and an important notion with spectral triple is the one of Morita equivalence. So we say that if we do have an algebra, a Morita equivalent algebra to that is an algebra B that can be written as endomorphism over the algebra A of this curl E, that is a finite projective A right module. So now imagine that you have a spectral triple, and you want to consider another spectral triple constructed on a Morita equivalent algebra. So the question is, can I transfer the structure of a spectral triple from my algebra to a Morita equivalent algebra? And the answer is yes. So the Hilbert space is just the tensor product over A of the initial Hilbert space and this finite projective module. And what one has to be a bit careful is how to change the operator D. So this D prime is going to be, of course, part involving D. And that's fine, because if you look at the Hilbert space, the second factor is just age. So I can imagine that on the second piece, I'm acting with the initial operator D, because D is an operator over age. But what it's a tricky part is what happens to the first factor. And so the second ingredient that is needed is an Hermitian connection. So each time you have a spectral triple, given two ingredients, so finite projective right module and an Hermitian connection, you can construct a new spectral triple whose algebra is Morita equivalent to the algebra you started with. So, of course, natural question is what happens if I do apply this construction to the algebra itself? Because clearly every unit algebra is Morita equivalent to itself. And then, of course, the finite projective model is just A self, and the algebra is, again, A. So by applying the previous construction, so this one is, again, A. So for age prime, this will be the product between A, tensor product over A and age. So it's, again, age. The only difference appears with D prime. So D prime turns out to be the sum of the D I started with and an element omega that has the form that you already saw earlier. So it's an inner fluctuation of the operator D. And these are the right candidate to be my gauge fields. And this is somehow the recipe to construct a gauge theory starting from a spectral triple. So somehow the idea is that by applying this self-Morita equivalence, I'm not changing the algebra, I'm not changing the Hilbert space. So somehow I'm considering that whatever I'm doing to my operator is just equivalent. So the configuration space is going to be made of these inner fluctuations. We already saw that what makes sense to be our action functional is the spectral action, because that's the only element that can be physical, because it's the only one that speaks about the spectrum of D. And for what concerns the gauge group are just the unitary elements. And you can see, of course, by conjugation with the unitary element, the spectrum doesn't change. So you see immediately the invariance of A0 under the action of the unitary elements. Okay, so of course the question is, does that describe any physically relevant model? And the story starts already in the 90s, where Kahn noticed that as soon as you take two copies of your canonical spectral triples, so you're really taking the product between your space-time and 2 points, that already gives a model that is quite interesting and gives you some kind of the Higgs boson appearing. And the story continues. So the spectral action principle was the step 2 of the story. So this introducing the spectral action. But definitely a groundbreaking result was due to Shamsuddin Khan and Marcoli that described a full standard model of particles with neutrino mixing and few characteristics using spectral triples. And what they obtained was to be able to write the full Lagrangians of the standard model using these ingredients. The thing to remark is that is actually the classical action. So it still needs to be quantized, and still means like nowadays it still need to be quantized. So that's the mental picture. So you do have a product of 2 parts. You have your canonical spectral triple that describe the gravity, and you have a finite part that describe the particle content. And as said earlier, for example, for the gauge group, the gauge group is given by the unitaries, and you see that this choice of algebra is what gives you the gauge group of the standard model. And the Hilbert space is not particularly enlightening, it's just 96 copies of C, and this describes the 96 particle in the standard model. And then you take the product, and by looking at your inner fluctuations of your new operator D, you find these gauge fields of your theory. And then the action is given by these two parts. So you have the spectral action. As I said, so this is the bosonic content. And then you have a part that is actually this fermionic part. And yeah, so as I said, so if you do perform, this 8-kernel expansion, this S is the one giving you the full Lagrangian of the standard model. Yes, so now just to already draw your attention on the fact that there are two notions of actions. So the the bosonic one, so the spectral action, we already discussed that. And the fermionic action is actually pretty interesting because indeed it deals with the inner product of H. And what is important is that it allows to impose the Grossmannian nature on its element. And if you remember in the first part of the talk, I was describing you the BV construction and how what one has to do is to introduce this ghost, and that ghost can have Grossmannian parity. So you will see that indeed this fermionic action will be used in the following to deal with the ghost of Grossmannian parity appearing. And as I said, so the idea is that you can get the full Lagrangian. Of course, small thing to remember is that, for now there is a bit of the compact issue because, when you're dealing with the canonical spectral triple, you have an underlying manifold that is asked to be compact, and that doesn't really work well with causality. And of course, we are in Riemannian signature, while for doing physics, we would like to go in the direction of Lorentzian signature, but at the moment it's a bit missing this story. Yes, so just for saying that research didn't stop in 2008. There have been a lot of models, a lot of people trying to go beyond the standard model, also because we know that indeed we need to go beyond that. And what possibility is, for example, going in the direction of these Patti-Salam models, where the gauge group is a bit bigger than the classic U1 times SU2 times SU3. Okay, but now let's go to our setting, so the finite case. I hope that what I just described you, so the fact that indeed you can describe the full standard model as this product, so product of a canonical spectral triple and a finite one, convince you the fact that the finite case might look simpler, but it's actually very interesting from a physical perspective because it's the part that encodes the particle content of your theory. Then we want to study the BV structure for gauge theory induced by a finite spectral triple. So what are the goals and what are the questions? So the idea is that we're wondering whether the BV construction can be described fully in terms of spectral triples, and whether the cohomology entering the story can be also understood and related to cohomology theory appearing for spectral triple. So said that graphically, we want to complete this diagram. So you see, I just explained to you how, given a spectral triple, this induces a gauge theory. And in the first part of the talk, we describe this underlying part where the first step was introduction of ghosts, and then the auxiliary fields, and then finding the Lagrangian submanifold where you want to integrate. And to all these steps, there were cohomology associated. Okay, my goal is to lift all this entire construction to spectral triples and really to find a description of the BV construction in this setting for spectral triples. And of course, this construction should be done in such a way that each of these new spectral triple will induce a cohomology, and this cohomology has to correspond to the cohomology coming from the BV construction. to just completed the diagram. Okay, so where we are starting. So we start with this finite spectral triple, and as I said, each spectral triple induces a gauge theory. What is the gauge theory induced in this case? So if we take as algebra just matrices and we compute the inner fluctuations, the result is just an affine space. For what concern the Hilbert space for the spectral triple, this is just a Cn, and clearly a self-adjoint operator in this context is just a self-adjoint matrix. So if you perform this construction, apply this recipe, you will see that your action as 0 is just a polynomial in your variable. So your configuration space is an affine space. So this S0 is just a polynomial in these variables. And the gauge group is UN. So let's try to see, of course, not any polynomial works. So we want that this is invariant under the joint action of UN. And this implies that the only option is that this 0 is a polynomial in the Casimir operators. So to give you the feeling, so if you do consider the classical, so the quadratic case, your S0 is this kind of structure. You see, I mean, all the variables, x1 all the way to xn squared minus 1 appear squared. And the idea is that, of course, it should tell you how you pass from self-adjoint matrices to AN. So the way I use is to have the identity corresponding to the last variable. So you see that this one is somehow containing the SUN invariance, and this one is just the identity. But if you try to describe that graphically, you see, of course, remember we are looking to the critical locus, and the origin is the only trivial orbits for the joint action of UN. And it's trivial orbit, it's a point, it's isolated, it's regular, not a problem at all. But what happened for any other critical point of the action function? So if you do consider any other critical point, so that is not the origin, the action of UN over that, it creates an entire orbit of not isolated critical points. So we are exactly in the situation that requires BV. So no way to escape. We have to find a solution. And the solution is that, okay, let's try to complete the first square of the diagram. So here we are searching for a BV spectral triple, so namely something that allows us to contain the ghost, the anti-ghost, all that gadget that we added here at the level of the BV construction with this X tilde and S tilde. So, of course, a few things to remark is that the natural context where you speak about finite spectral triple is over C. And S tilde, we already saw that it should contain Grassmannian variables. So to solve the first problem, is not really a problem, but the first point, we need to go from C to R. So this is somehow calling us for the introduction of a real structure. And here I'm just recalling the definition of a real structure. So it's this antilinear isometry over H. Second problem, the appearance of Grassmannian variables. I already pointed out that actually we do have two notions of action. And here I briefly recall them. There is a spectral action, and the fermionic action is the one that actually allows us to impose a Grassmannian nature to the element in the Hilbert space. So putting all these things together means that if we are aiming to lift the BV extension at the level of spectral triple, we are expecting to go from an initial spectral triple to this BV one that turns out to be a real spectral triple. So we are expected to add a real structure. Of course, the question are, where do we put these ghost fields? So which role the ghost fields are going to play in the new spectral triple? And also, where can we extract the information from the initial spectral triple, informations like how many do we need, up to which ghost degree, and so on and so forth. So all this information should come from the initial spectral triple, and we should find a way to extract them from there. Second question is about the extended action. Similarly, we want to be able to find a way to determine our S tilde just from our initial package. And here is the notion, what is for me a BV spectral triple? So as already said, I want it to be a real spectral triple. And of course, what is going to play a key role is the fermionic action. So we are considering this fermionic action defined over half of the Hilbert space. And this Hilbert space is asked to be a Z-graded vector space. And you might recognize here that I'm imposing the same kind of doubling situation we do have for a BV theory, because we still need to have ghost and anti-ghost. And then a spectral triple in this kind of properties, so a real structure and a Hilbert space that has this kind of doubling is a BV spectral triple associated to my initial one if it satisfies this condition. So if I do define my X tilde to be made of this sum, so my initial configuration space and then what comes from this Hilbert space, and if I do define this S tilde as my initial 0 plus this fermionic action of this new BV spectral triple, then I can say that this new pair X tilde S tilde is indeed a BV theory associated to my initial gauge theory. So let's go graphical.
Sorry, F stands for finite or what?
Yeah, no, it's not finite. So it's so you're divided in two. So this Hilbert space, you want just the part that respect. So it's like the
I understand Adam's problem, because you use an F as a function, and then you use an F here as a subscript. So yeah, indeed.
Yeah.
I mean,
right. Oh yes, thanks for the feedback. Of course, I'm not noticing that anymore, but I see the confusion. No, it's describing the half of the Hilbert space that corresponds to the part that is self-adjoint with respect to J. So the Hilbert space is complex, and I need to divide that in two to get like the real part, because this needs to be describing my ghost. So physics, we go for the reals and not for the complex. So it's just half of it.
Okay, but after all, this F is this cutoff function, or?
No, sorry, I realized that no, sorry, this F appearance as a subscript is not related to the previous one. I'm very sorry. That's creating confusion.
Okay, but this is not at all any parameter, yes? This small subscript F in this definition of S fermionic, yes?
So it's so the idea is that you are defining your F fermionic only on half of the Hilbert space. It's just, the Hilbert space is complex. You have the real structure acting on that.
Okay.
And, part of the vectors will be, if you apply J over them, would be the identity, or, if they would go to the conjugate. So it's a parity conjugation, the charge conjugation. So it's, you're splitting the Hilbert space somehow.
Okay, but maybe the problem is between semantics and syntax. So this F only indicates the fact that you are performing this construction, this halving, yes?
Yeah, correct.
so F stands for fermionic, maybe.
Yes.
Okay. Yeah,
But
thank you.
I do agree on. Thanks for noticing that.
Okay.
Yeah. So what I wanted to show here is just how.
Sorry, Roberta. I'm still. I know, but you're already over time. But I'm trying. This is like a key definition, and I'm trying to understand it.
Mhm.
And for me, it's kind of ignoramus per ignorabimus, because you define a BV spectral triple by saying that blah 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 is a BV theory. I don't get it. So, what really the conditions are? What does it mean to be a BV theory?
Yes. So you want this X tilde to be this Z-graded vector space that allows as this doubling. That in degree 0 as your fields, and for your S tilde you want that is a solution of the classical master equation, so that the Poisson bracket of S tilde with itself is 0. So what you're saying is that if you do take your x tilde in this way and your s tilde in this way, the result is indeed a pair where your S is solution of the classical master equation. And this is what you're asking somehow, yeah. So proving that a BV that a spectral triple is a BV spectral triple entitles to check that this x tilde is this Z-graded vector space with doubling ghost anti-ghost, and that this S tilde has all the needed property, including solving the classical master equation. This is how you prove it.
But I'm also confused. Here you have a initial spectral triple A0, A0, D0. And then I go to this line and everything looks classical, X0, S0. So are they spaces or? I don't understand the relation between this AHD and then XQ.
Yes, so okay, maybe here the diagram can help. So this is the initial spectral triple.
Yes.
And so this X0 is is defined to be your inner fluctuations. So is your gauge fields. So this
okay. Now that answers my question. Okay.
And your S0 is just the spectral action. And once the way how, given a BV spectral triple, you construct a BV extended theory is by looking at the Hilbert space. So the Hilbert space is the one providing you with the ghost sector. So this HBF is representing the ghost and anti-ghost sector. And then is this new operator, this DBV, that is the one that determines the fermionic action. A fermionic action describes the extra bit that you need to add to S0 to obtain S tilde. So you see that the way how you constructed the gauge theory from the initial spectral triple looks more to the algebra and to this spectral action, to the spectral aspect of the spectral triple, while the way to encode this the ghost is by looking to the fermionic action, but that's somehow natural. We're adding Grassmannian variables, so we're adding fermions. So it's actually quite intuitive that the right ingredients to consider is the fermionic action. And then, of course, the fermionic action is defined on the Hilbert space and actually half of the Hilbert space. So it makes sense that my ghost sector is actually determined by the Hilbert space.
But how come you have that X naught and X naught star shifted as the structure of the Hilbert space? So is X still like Hilbert space? In which category you have this addition?
Oh no, I mean here we are just in a finite dimensional case, so we're speaking about matrices. It's a finite dimensional case.
But we are looking at okay, fine, but even in finite dimensional space, Hilbert space is a bit more structured than the vector space.
Yeah, I mean, maybe I can show it how it look for the example. So I hope that this clarifies a bit.
Because I just want to know in what sense I'm supposed to think about X tilde. Should I think about X tilde as a Hilbert space or a vector space? In what category should I view it?
I mean, when you speak about this BV theory, you are not really making use of the inner product explicitly. So remember that the context where I described that to you is this setting of graded manifolds. And if you're in the context of fully flat graded manifolds, these are just graded vector space. So your drop-ins, of course, for the spectral triple, you have a richer structure. So you also have this inner product, but it doesn't appear in the structure of X tilde. So you just need less structure to define it. I don't know if we can make use of that later, but just for having a BV theory, you're not dealing with the inner product structure.
But okay, so now you have this X tilde defined above, and now you have a different formula for this X tilde below. So does it mean that you have some equality?
No, sorry, I was a bit more explicit in this X tilde. I was defining things divided by gradient, but you see here above. So
I just substituted. Okay, thank you. Yes, okay. Yeah. Okay. So did you define this BV extended theory? Is it defined somewhere earlier? I just missed it.
What? Sorry, this one?
What is the meaning of being B, the extended theory? I know you answered my question, but did you write it somewhere earlier in your slides?
Oh, yes, it was a few slides. Should I go back or?
Yeah, just for a few seconds, if you don't mind.
Sure. Sorry.
Four so far.
Yeah.
No wonder I forgot.
Yeah, sorry. Okay. It's almost. It was the one where the subscript one confused you. So here. So these are the conditions for your X tilde. So it is a C-graded supervector space with this doubling anti-ghost.
Okay, thank you. Yes. Okay, no wonder I forgot. It was 20 slides ago.
Yeah, sorry. Let's see if I now can find where we left. Because at least I wanted to show you the example. So the model I've been.
By the way, you have minus 10 minutes left.
I'm super sure. I know. I'm. When you said 90 minutes, I overestimated the 90 minutes.
Yeah. It looks like a lot of time, but okay.
Yeah. So how is the construction for the model? So for the algebra we are starting with is just the matrix algebras. And what is interesting to notice is that the algebra stays unchanged. And this fits with what I just said. Somehow the algebra describe the physical fields, and we are not adding any physical fields. That's fine. So the big change appear for the Hilbert space. So the Hilbert space, so in the initial spectral triple was just the Cn, and we are enlarging it a lot, adding this ghost and anti-ghost. And what works for this model is having, going from Cn to 4 copies of n by n matrices. So that are divided in degree 0, degree 1, -1, -1, and -2. So in this green box, I'm keeping fields and ghosts. And in the orange box, I'm putting the anti-fields and anti-ghost. And of course, I should divide that, it's complex, it's too big. So the part that is going to enter the fermionic action is just these 4 copies of SUM. And what is interesting to notice is that it's actually fully determined by considering this quotient of the unitary element of your initial algebra, quotient with respect to the center. So if you want, so this was the way to extract this information. So which ghost do we need from the initial spectral triple? You look to this quotient, unitary element of the algebra over the center. So here I just write explicitly if you want to have a bit of a feeling, so you're just big vectors. And the Hilbert space is really the one containing the ghost in the ghost sector.
And just double checking these subscripts -2, -1, 0, 1, they are not footnotes anymore.
No, these are the degrees. I want to keep.
I was joking, yes, but these are not footnotes, okay.
No, not this time. There are no square brackets, so they're not.
Well, there are square brackets, but somewhere else, yeah.
Yes, that's true. So for the Dirac operator, and so it's so you see here is divided, so it's a square as a block matrix. So the idea is that it acts on ghost and then the anti-ghost. So this top corner here would be something acting on on anti-ghost and sending them in anti-ghost. So it has this, of course, like self-adjoint structure, so that it's needed for a spectral triple. And then this operator can be described in this way, so as the adjoint action of the ghosts or the fields. And if these are the different blocks for what concern each term in this matrix, they are determined by the structure constant of SUN. And somehow to give you the feeling, so there are constraints on how this Dirac operator can look like, and there are like proper way of determining it. So, or say that differently, how given the initial spectral triple, we can construct this D and then this extended action. So, for example, this fact of having this 0 at the top comes from the fact that you expect linearity in the anti-fields. And this comes from like the BV construction. The fact that if you look, for example, this block matrix R and the block matrix S, you see that there is some kind of anti-diagonal condition. So you see that in the anti-diagonal depends on the same field or Gauss field. And this is just the degree condition. You want your extended action to have degree 0. Then once we do know the big structure of this matrix as block matrix, and we know the final structure of R and S, we just have to describe the single components, and this, as I said, comes from the structural constant of SUN. And of course, the idea is that indeed this operator dBV is what determines, the remainings, the parts that we have to add. And so it determines the fermionic action and this BV action. And then, of course, the last thing that we need is the Via structure, but that's not very surprising. Okay, so of course, now we are over time, I know, and so the theorem is just say, okay, you want to prove that this is indeed a nice final spectral triple, and the theorem is that indeed it defines a BV spectral triple for our initial theory, and the proof consists just in checking that indeed this S tilde, X tilde, and S tilde satisfy the needed properties. And this somehow complete the first step of the construction. And, the remaining that I can tell you is, of course, whether you can go over. And you can continue.
Sorry, Roberta, sorry, I really don't understand. What is this?
Oh, sorry, that's the initial of my name. It's my theorem. Sorry.
Ah, wow, you are really tricky. Footnotes, your initials, and if you wrote, RAI, I would understand that it's maybe your initials, but when you write this I'm completely confused. Okay.
Okay, I will keep. I will take a note for that, and so, thanks for noticing. Yeah, sorry, it's just the result of indeed proving that this is a good BV spectral triple for our theory. And what I don't have time to tell you is that, of course, one can continue, because as any BV theory induces a BV complex, one wants also to check what happens for the spectral triple. So I can just maybe flash the thing. So, of course, you can have cohomology associated to these BV spectral triples, and this is actually reflecting the BV cohomology. It's a bit complicated. The result is that you should consider Oshild cohomology for a coalgebra, and you have a bit of the shifting because that was the shifting on the Gauss degree. But maybe, here is how you determine that, and that, of course, is again the Hilbert space that determines your coalgebra. The algebra that gives you the co-module, and then if you look to the spectral action, the part in degree 0 gives the co-module structure, and the part in a degree different from 0, this gives the co-product, and then there is this isomorphism of complexes. But sorry for, that says that you can also consider the auxiliary fields. That also works, and somehow that's the final part of the story. So we can complete the diagram. So we mostly discussed the first step on how you can construct this BV spectral triple, but as I was mentioning, also the addition of auxiliary fields fits this kind of diagram, and all this spectral triple induce a complex that is this Oshild complex for the coalgebra that really is quite isomorphic to the BV complex. And the result is that, of course, so we determine how to extract information from the initial spectral triple and to construct in this BV extended one. We established what is the role of the ghost and the anti-ghost, and what is the role playing in the BV spectral triple. So the ghost sector is generated by the Hilbert space. We figured out indeed also what happens at the level of cohomology, and the hope is that having a more geometric way of representing this BV cohomology, there might also be more technique of computing it, because at the moment it's very difficult to compute it. But then what is even more important is that we obtain an action that is suitable to be quantized. So this is why my talk was called like a first step towards quantization, because as you know, so the idea was of performing this BV construction was really to give us a new action that can then be quantized via this stationary phase approximation. And of course, this is just for finite spectral triple, so way more has to be done, and that's for the future. And sorry for going over time.
Okay, thank you very much. Alessandra Frabetti, my goodness, I haven't seen her for decades.
Yeah,
Okay.
yeah, she is now a lot in this higher higher structure word. So we are trying to find a definition of a spectral triple with the higher gauge groups. Let's see.
Okay, so these are your projects with these people, or these are projects of these people?
No, I'm working on this project with these people. That's it.
Okay, this looks very good. So you have Krasetsky, you have Perez Sanchez, okay, fuzzy geometries, Chern-Simons, higher groups, that's Alessandra, and Richard Nest, non-commutative manifolds. Okay, this looks very interesting. Could you please go back to the previous slide? Okay, so let me ask some quick naive questions. So first, I mean, we are saying that you have a BV spectral triple associated to the initial spectral triple. So your choice of the article, indeterminate article A, does it mean that you can have many different BV spectral triples associated to the initial one? Is it like some choice, or is this construction more or less canonical? I'm still, trying to grasp it.
Yeah, I mean, so the idea is that you're adding all these extra variables to allow you to have some space for deformation. Of course, you can be redundant and add in even more variable, not using that. But somehow it's canonical because it looks to the gauge group and the symmetries of your theory. So this is why I was saying like the ghost sector is determined by looking to the unitary of your algebra, so to the symmetries, to the gauge group. So it's not unique because you can always overdo, but this choice is a good choice. So you put what is needed and not too much. So
this is a very good answer. I really understand it now. Thank you so much. This is very, very good. Now, what is the total spectral triple or total theory? This I missed. What? How do you obtain
that's so I was telling you that there was a bit of a technical step that you still have to add some auxiliary fields that are only needed to be able to find this Lagrangian submanifold in some kind of canonical way. So it was these auxiliary fields were added in a way that were not interfering at all with the cohomology. So they were added as contractible pairs in cohomology. So it's just a technical step that is needed for indeed finding this Lagrangian submanifold. But of course, for claiming that we can perform the entire BV construction in this setting of indeed spectral triples, also this further extension should be still suitable to be encoded in an object that really looks like indeed a spectral triple and is still induce a cohomology exactly as the BV spectral triple does, and still there is this kind of quasi-isomorphism with the complexes. So of course, it's more technical for arriving to finding the Lagrangian submanifold, but it's needed to claim that indeed this kind of approach works all the way to the end.
Okay, so I'm done with my questions, but let me also add a comment. The comment is for Adam. I just couldn't resist reading about supersymmetry when you asked your question, and I found a very interesting remark. In 2021, supersymmetric quantum mechanics was applied to option pricing and the analysis of market in finance and to financial networks. So, with supersymmetric quantum mechanics, you can just make money on the stock exchange.
And the symmetry is when you lose money, yes?
Anyway, I found it really shocking, so I thought I would cite it to you.
Oh,
I would
thank you,
never
thank
have
you.
a dream of supersymmetry being applied in financial markets. And as everybody knows, Sheldon Cooper got his Nobel Prize for superasymmetry, right? So that's you can have many jokes around it. Okay, I also was trying to find out about this KO homology. There is even some Baum-Kohn conjecture in the real Baum-Kohn conjecture involving KO homology. And sometimes instead of saying real K theory, people say KO theory. So I believe these things are paired; they are just dual. So. I think it was correct what I was saying, but I still couldn't extract a rigorous definition of what is KO homology. So that's a bit disturbing, but okay, that's definitely done somewhere. Okay, I'm done with my questions and comments and jokes and whatever. Are there any real questions or comments? Adam, Ali?
Yes, I would like to ask, maybe it is a naive question, I don't know, but in this choice of this cutoff function in spectral action, how do you think about it? Should it be somehow motivated by physics or by pure mathematics, by pure reasoning? I don't know.
You mean F or you mean the
Yes.
cutoff lambda?
Yes. I mean this. Okay, this is another interesting question about this energy scale, but let me first start with F.
So the idea is that okay. So first of all, F should be a function that allows you to compute a trace. So in
Yes.
that is a function that makes your operator a trace class operator. So this is what is needed. Now, for making comparison with physics, so the idea is that you cannot make a direct comparison between your spectral action and the action of any model, any physical model. There is a passage to take that is this it-kernel expansion. So only after you make the it-kernel expansion, so you start from your spectral action, make the it-kernel expansion, and then what is your result is what you compare with the physical models. Now, in this passage from the spectral action to the it-kernel expansion, the only thing that survives of this function are the moments. And of course, I mean, if you want to make comparison with physics, you're probably putting yourself with the canonical spectral triple as basic, and then you're putting like finite ones, and you're taking this kind of product. So if you do have your spectral action on a canonical spectral triple, then the moments you're getting are actually 3, because your manifold has dimension 4, and what survives is the moment 0, moment 2, and moment 4. So then it's just 3 numbers somehow. And if you apply this kind of procedure for example, the result of Shamsuddin Khan and Marcoli for the standard model, what you do have is you consider the spectral action on almost commutative manifold, so canonical times a finite spectral triple. And then these 3 parameters are used and are interpreted on the physics side as the cosmological constant, as the coupling constant at the unification energy, and so on. So are these the kind of physical numbers that enters? So you see that the informations of the function is really diluted. Is only these three numbers remaining. So this is why also in the construction this f was not appearing too much, because you're not really able to extract from physics much information. So, or differently said, they are not so relevant. It's just important that it's a function that has the right moment and that it allows you to have a trace class operator. So those are the constraints.
Yeah, but maybe still there would be some a priori reason to postulate some form of this f, and then magically this constant would somehow agree with experiments. Is it possible, or it is a kind of I don't know, too high hopes?
I mean, for example, so there are good reasons for thinking that there should be like a d square so that the Laplacian is appearing. Of course, we are in Riemann signature, so it's the Laplacian. But if we just put that under the rug, I mean, in physics you have the D'Alembertian appearing, which is the Lorentzian version of the Laplacian. So you do expect that there is a square in that f. That makes sense. But it's mostly done, in the other direction. So somehow, just checking that the right moment appear. And so a priori, what makes sense is to expect like the appearance of the Laplacian. Yeah.
Okay, and also your comment about this energy scale. So this energy scale would be something like a standard model energy scale, or you going even further into Planck regime, or?
I mean, I think that the entire idea, so, speaking about, dreams, is that we are trying to quantize gravity. So then, this kind of approximation works in this dimension. But of course, at this point, it's very theoretical. So it's, and then, I mean, for example, the fact that of having the momenta, so one of the momenta being the coupling constant at unification scale. So that's already telling you what is the unification, even though we know that they're not really, unifying entirely, but almost. So that's the scale and the regime you put yourself in.
Mm-hmm. Mm-hmm.
By the way, you just reminded me, Adam, with your question, that there was some time ago, sorry, I remember it very vaguely, but in the work of Kohn and Shamsuddin, they predicted some masses, and then there was an experiment who ruled out exactly the masses predicted by this. Can you remind me what it was all about?
Yeah, that was the mass of the Higgs boson.
Higgs boson, yes.
So the idea is that so I told you that one of the first model was this, let's take two copies of the space-time, and then they found the Higgs boson as inner fluctuations coming from this internal space. And then if you actually compute, the spectral action and then take this it kernel expansion, you find the Lagrangian. And the mass is the coefficient that appears in front of the term in the Lagrangian. So of course, if you do have, this inner fluctuation that is your Higgs boson, it appears also in your spectral action. It appears also in the it kernel expansion of the spectral action. So they had this prediction that was exactly that coefficient appearing in the function. And they didn't find the right number, but they actually after that they corrected it. So there were different solutions, and one of the solutions was to actually add an extra scalar field that is used by sigma. So it's an extra parameter that one can tune. Or another option was to weak the first order condition, and also that helped. And then there was the third possibility that was considering larger algebra. So a solution has been found, but yes, so the prediction was a bit wrong. Yeah. But the point is that it was only based on having these 3 numbers and tuning them. Makes sense.
Yeah.
It's not super precise.
Yeah, thank you so much. Anybody else? Ali, do you want to ask a
Yes,
question?
I have a short question, maybe a short notational question about the slide number 27. Could you please bring slide number 27?
Yeah, sure. Okay.
Yes, my question was that is there any reason for this tensor C? Because M2C is a matrix, is the matrix algebra of complex with complex entries, and is there any special reason for writing tensor C? Because M2C tensor C is equal to M2C, and in reality, when you consider M times 2-pointer space, the corresponding non-commutative space is C infinity M tensor M2C. So I didn't understand what is, maybe it's a kind of typos or miswriting, or I'm missing something.
Yeah, no, I mean, I think that is related to, how you want the Higgs boson. But I mean, written like that is not self-explanatory. You're right. So it might be even a bit confusing. But you see, I mean, this picture somehow wants to tell a bit of the story. So this line is the Higgs field. So you do have these 2 copies of your space-time, and the inner fluctuation of the 2 is the Higgs boson, and this was what appeared for the first time, taking these 2 copies. And then of course things got a bit more complicated because you want to have more than just the Higgs boson. And this is why you go to something that is more than 2 points, and you add all the rest. And actually, there is already taking the colors into account.
Mm-hmm. Yes, and another question: what papers of Kohns you're referring to in the paper 1990? Do you remember the paper of Alan Kohns you referred here? The first reference you are writing here. Do you remember the title or any particular paper of Kohns?
Not at the top of my head. I think I should have that in my article, but I don't remember the.
Okay, I will search in the internet. And my final question, you pointed out that there is no natural category structure on the space of spectral trips. It was a very interesting point, but I mean that, what do you mean precisely, but non-existence of a categorical structure? What kind of abstraction exists to we consider a kind of categorical structure? Because in the category of smooth manifold, because we have a category of a smooth manifold, and maybe we have a categorical structure for the space of Riemannian manifold, but we should modify this idea in the non-commutative case. So I'm really interested to know, what do you mean by the non-existence of categorical structure on the space of all spectral trips?
So what I meant is that the natural idea would be to take your spectral triple as object and then look for morphism between spectral triple. The problem is that if you look for like meaningful morphism, so you go beyond unitaries, then what would be your natural guess is actually not sending spectral triple into spectral triple. So it feels that as soon as you have an interesting notion of morphism and you apply that to spectral triple, you're getting immediately in something that is more general. So this is why so the problem is really in finding the right morphism that goes beyond the super trivial ones, but still gives you spectral triple. And apparently that was not, the people working on that felt that was not the right strategy to go. So it felt more natural to extend and not having only spectral triples, but thinking the spectral triples as a trivial example of these KK cycles. And the KK cycle is the context where this, for example, this KK product has been defined. So particular example of KK cycles are the spectral triples, but you know, they can be way more general. So up to my knowledge, what people are currently working on is finding the perfect tuning between, you know, having an object that is interesting, that generalizes spectral triples, and for which one can construct a morphism that would be internal in the category. And that has a huge analytical issues appearing.
Yes, I see. Okay. Thank you very much for your very interesting talk.
Sorry, may I have one more question?
Yeah.
And maybe before question, maybe comment to Adi. I believe that well, if this paper is from 1990,
yes.
So probably it would be maybe Kohn and Lott.
Exactly. This is exactly what I wanted to say.
Okay.
Kohn and who?
Lott.
John Lott.
L-O-T-T.
Yes. At the same year. Yes, that's very good. Thank you.
So, Roberta, do you think it's Kohn Lott?
Yes.
It could be. I think that there were a couple of different papers. So definitely Kohn Lott was one of the first models going in this direction. I don't remember whether that model had already some extra ingredient. So it was a
double-sheeted spacetime. That's the idea from Kohn Lott. I remember it very clearly.
Yeah.
And I don't think there was any preceding paper, and somehow I don't remember any follow-up by Kohn alone. So.
Oh no, that I know for sure that there are only one paper together with this kind of model described. Yes.
Okay, so yeah, Adam, I fully agree. I had exactly the same idea.
Okay, and
yes, thank you, Adam, for the reference.
Okay, thanks. But maybe one more question about this notion of morphism in the context of spectral triple. So my question is whether is there any agreement how this morphism, this notion of morphism should look like even in commutative case? Since already in this commutative case, I'm not so sure whether there is a general agreement. So you want to preserve everything, also Riemannian metric, also the spin structure, or maybe just like a diffeomorphism of smooth manifolds?
Yes, in the commutative case, maybe we should only consider the diffeomorphism which preserve the Riemannian metric, namely only the isometries, and this would be very restrictive.
I don't know, since okay, there are spectral triples not satisfying this last irreducibility axiom, and those okay, you can construct spectral triple with general Riemannian manifolds, and if you don't have a spin structure, you cannot preserve it. So I don't know what is already at the commutative level. What there would be the right notion of morphism?
I guess the idea would be that you take something like a closed Riemannian manifold, which is, you know, oriented and everything, and you take a smooth map and you see what it does to the structure. If your spectral triple is this canonical one coming from the Dirac operator, maybe everything is automatically preserved if your map is smooth. No, I don't know.
No. You can have diffeomorphism, which is not an isometric.
But why diffeomorphism? Forget diffeomorphism. We are talking about maps between different spectral triples.
No,
but diffeomorphism.
Piotr, but still, even if you have diffeomorphism, it could not respect metrics. Yes. Yeah,
of course. So you want metric preserving.
Yeah. So that's the reason why I'm not so sure, even in the commutative case.
Yeah, I mean,
it's like established. It should be well known. I mean,
And maybe one last silly question. At the beginning of your presentation, you have some picture that going from differential geometry, and differential geometry was represented by some picture of something like a surface, and then to non-commutative, and there was some picture of some nodes. Could you tell me what are those nodes?
Oh, no, sorry. I was just somehow trying to represent algebra. So it was just this kind of
Okay.
going from something that is nice and can be somehow drawn and you can have an idea, and then something that is just really abstract. So that was somehow the kind of message I was trying to give across.
Okay, so this page, there are some writings on this page, but you don't guarantee that those writings refer, in fact, to non-commutative stuff. Yes? Just
No, I wouldn't bet my life on that. No.
okay. Okay, thank you. Thank you for the beautiful talk.
I discovered some cave of some archaic writings on the cave walls, and Okay, let's wind it up. Do you have any questions? No. So let's thank Roberta, Anna again. Thank you.
Thanks for your patience.
And I stop recording.